It should work now, yeah?
Yeah.
Good. So I would like to thank organizers, especially Professor Murat Bavarslan. I know him for a long time, and it was a pleasure to meet him again, and also other people, other colleagues and friends. So thank you for this invitation, and it is my pleasure to talk in front of you. So my talk is related to my research done in the last maybe 5 or more years. So it is related to magnetic curves, magnetic maps, and vector fields as magnetic maps. Or instead of magnetic maps, we can use also the terminology of harmonic maps with potential, and I will explain you why. Okay, so the outline of my talk is first I will talk about the Landau-Hall integral or the Landau-Hall functional. This introduced initially for curves and then for maps. And then I will focus precisely to the topic of this talk. Okay, so let me briefly start with geodesics. Thought as a solution of a second order nonlinear differential equation called Euler-Lagrange equation of motions. The idea is to consider the kinetic energy. So we have a curve gamma. I didn't put the limits of the interval here. So we consider the kinetic energy, and we do variation of this curve, and we consider the critical points, and we get geodesics. If we consider local coordinates, the Euler-Lagrange equations are written in this way. So here is a second order differential equation, ordinary differential equation. Here are the Christopher symbols of the Levich-Vita connection.
Sorry, Professor. Sorry, we just see your cover page. If you show something.
Yes.
But now we are in the first page. We didn't see the next page.
Let me see why. Now?
Okay, now it's okay. Thank you.
And now can you see how I move?
Yes, we are seeing now. Thank you.
It was something blocked.
Yeah.
So, okay, thank you for this. Okay, so this is a kinetic energy, and we will consider the variation of this curve, which we want to be a geodesic. Okay, and if we consider the variation of this integral, we obtain the equation of the geodesics. Okay, so these are Christopher symbols, and if we think we can express in terms of the Lagrangian. So here is the Lagrangian, and these are all the Lagrange equations. Everybody knows this. Okay, and now what we do in order to obtain magnetic curves, we make a perturbation of the kinetic energy. So this part comes from the kinetic energy, and we add a potential. Okay, so what does it mean? We are working with a potential one form called omega, and this will be applied to the velocity, gamma prime. And this new functional is called Landau-Hall functional. And we will make the variation of the curve, and we consider the first variation. So the derivative of the Landau-Hall functional with respect to the variational parameter. And what is this variation? In fact, it is a family of curves, or a map from AB cross, this is the interval of variation. and such that the ends are fixed. And for 0 here, we obtain the initial curve. And here the parameter will be called epsilon. And if we make the derivative with respect to this parameter, we obtain the variational vector. And because it's with fixed ends, this variational vector is vanishes at the end. Okay, and once we have the lambda whole functional and we consider the first variation, so we consider the derivative with respect to epsilon and compute at epsilon equals 0, we obtain this equation. And V is arbitrary, okay, the variation is arbitrary. This implies that this quantity should be 0. So a critical point of the lambda whole functional leads to this part be 0, okay? And this equation will be called the Lorentz equation. Okay? In fact, all this terminology comes from physics. So if we work in dimension 3, everything is natural. And if we do here, this phi appears here. So what is this phi? So this phi is a 1-1 tensor field. Okay, so it's an endomorphism of the tangent space, and it comes from the potential. So if I go back to the potential here, doing the computation, the differential of omega appears. And as we see, this phi is nothing but the contraction with the inverse metric with respect to the differential of omega. Okay, so we have this relation. So the Lorentz force phi is obtained from the omega. And now everything can be thought a little bit more general. So instead to consider here an exact to form, okay, we remove the potential. So we think here to have a close to form, and phi can be obtained. And we think that we say that this phi defines the magnetic field. Okay, and the Lorentz equation, or the equation of magnetic curves or magnetic trajectories, can be written in this way. Okay, so it is acceleration here, and this force, this Lorentz force, applied to the velocity vector. Okay, and the idea is to solve somehow, or to interpret the equation of this, the solution of this equation. Okay, so some analogies with geodesics, because magnetic curves extend geodesics. I mean, if the magnetic field is absent, so phi should be 0. So we recover the equation of geodesics. And the existence and the uniqueness of geodesics remains true for magnetic curves if we fix the initial point and the initial velocity. And also the property of having the same energy or the same speed along the trajectory. Okay, this is an easy job to do, and gamma prime has unit length. In particular, if we consider to be 1, that means the parameterization is that natural. The magnetic curve is called normal. And there is also a difference, an important difference between magnetic curves and geodesics. The balance property of geodesics. You know, if you want to enlarge the interval, you have to diminish the length of the initial vector, or vice versa. This cannot be done in the magnetic background. Okay, some examples of capital F magnetic fields. in dimension to any f multiplied with the area element is a magnetic field, because if we take the derivative here, the differential here, you obtain a free form that should be 0. If we work in Kähler manifold, almost Kählerian manifold, the Kähler-2 form is closed. And this is for even dimension. And for odd dimension, we have the notion of the almost contact metric manifolds. And here we have as example, Sasakian, co-symplectic, and quasi-Sasakian manifolds, where the fundamental two form or the contact to form is closed. Okay, so these are very good candidates for studying magnetic curves. Okay, harmonic maps. So harmonic maps generalize geodesics. If this is one dimension, we have a geodesic. So what we can do for maps? So we have a map between two Riemannian manifolds. We consider the energy functional. So this is the energy. And if we consider critical points of the energy functional, we obtain harmonic maps. And this can be expressed in a tensorial equation. The tension field of F that is defined as the divergence of differential of F vanishes. Okay, so this is the equation of harmonic maps. This is a very important topic in differential geometry. And we want to do something to generalize. So let me see if I can. Let me see if I can. No, okay. I will return to this one. I wanted to put also a white table here, but it seems that doesn't work. So what we do have here, so we have okay, let me. Okay, let me try like here. So let's say here we have geodesics, and we extend to magnetic curves. Geodesics are extended to harmonic maps, and we want to close this diagram. So we want to define here something that we want to call magnetic maps. Okay, so our plan was to do the same trick as we did for geodesics. Okay, so I want to remove this. Okay, good. So we have the energy. We take the one form on the codomain in order to create the magnetic field. And we will take also a vector field globally defined on the domain. And we need it to be divergence free. So its divergence to be 0. And we make a perturbation of the energy functional with a potential. Okay, so this is the reason that magnetic maps are often called harmonic maps with potential. So how we consider the potential part? So we have psi here on n. We move it via the differential of f in m. So we apply f star psi, and we obtain something here. And for that vector, we apply omega. We obtain we apply the potential, and we integrate on n, because psi is defined in points of n. Okay, so we consider this functional associated to psi and omega, and we consider the variation. And if we write the variation equation, so this derivative to be zero, we obtain in the left part the tension field of F, because everything is so from the energy integral we obtain the tension field of F, and in the right part, so from the potential part, we obtain this expression. So here is the Lorentz force, and here is the differential of F applied to psi. And now, if we look at this Lorentz equation or magnetic equation, we notice that omega does not appear. So what we need here, the Lorentz force that comes from d omega. Okay, so d omega will be replaced with a closed form F. And it is a tensorial equation, so we can how to say, we can cancel the property of n to be compact in order to consider the integral, and also we remove the assumption for psi to be divergence free. Sometimes we keep it, sometimes we can remove, but in the definition we can remove it. Okay, so all these conditions can be removed. So we will consider a magnetic map that satisfies this equation. Okay, some examples. A constant map is automatically magnetic with respect to any psi and any closed form F. If n is an interval, and we put here t as a parameter, the metric, the most natural metric is dt square, and the psi is d over dt. And if we do everything, all theory applied to this task is we obtain the magnetic maps, extend magnetic curves. So magnetic map means magnetic curve. And of course, if magnetic field is absent, so F is 0, phi is 0, so tau F is 0, meaning that F is a harmonic map. Okay, so this means that with magnetic maps, we extend also magnetic curves and also harmonic maps. Okay, so let me give you only one situation when F is an isometric immersion. We'll return to this condition, and we'll see that this is very strong condition. If we ask also for F to be isometric immersion, we know that the tension field of F equals NH, where H is the mean curvature vector field of N in M. And this means that in order for F to be a magnetic map, we need this relation between psi, phi, and H. So this is characterization for magnetic maps that are moreover also isometric immersion. So it is really strong. Okay, this definition can be considered very natural in enormous contact geometry, because for example, if we have an enormous contact metric manifold, M, phi, xi, eta, g, almost all people here know this notion, and I will not give the definition here. And if we consider the identity of M, the identity map from M to M, and we ask it to be magnetic with respect to psi, this is the red vector field, and with respect to d eta, okay, so this gives a contact distribution, so we take the differential, And this is magnetic if and only if the interior product of d eta with respect to psi vanishes. But this is very natural condition in the Sasakian geometry. In the contact metric manifold, not almost, in contact metric manifold. So the definition is sustained by this very easy example, which is not trivial, but okay. So in order to pass to the second part of the talk, meaning vector field, I will recall some basic things about the tangent bundle and also unit tangent bundle. Also to fix some notations, we have the Riemannian manifold M, we have its tangent space, we consider the tangent bundle, the canonical projection. This induces a foliation given by the kernel of the differential, so we obtain the vertical spaces. We have a globally defined vector field that is called the Liouville vector field. Okay, so U are coordinates in the fiber, and the X are coordinates on the base manifold. Okay, G the metric, nabla the Levi-Civita connection, and we have the splitting of the tangent bundle of Tm. Tm is a manifold in this case, and it is split in the horizontal distribution that is defined via parallel translation with respect to the Levi-Civita connection, and the vertical distribution. Okay, we have the vertical lift and also horizontal lift. Okay, the vertical lift is defined here. The horizontal lift is the only one vector field that projects to X. So the vertical lift, the horizontal lift of X. Okay, so we obtain two lifts, and with respect to this lift, we can define a Sasakian metric on Tm. That means they preserve the length from the base manifold and make the horizontal and vertical part orthogonal. We can also define an almost complex structure, J, which maps horizontal to vertical and vertical to minus horizontal. And Tm, with respect to these two geometric objects, is an almost Kählerian manifold. It is very known. That means the two form omega s, the Kähler two form, is closed, and it can be considered as a magnetic field on Tm. So we will work with this magnetic field. And magnetic curves in Tm, we initiated a couple of years ago the study of magnetic curves in Tm and also in T1M. It is still developed. Recently I saw a paper using other metrics on Tm, G-natural metrics and so on. But we are interested in magnetic maps. So we take a vector field on M. It can be thought as a map from M to Tm, a section in the tangent bundle. And we may ask when psi, this psi, is a magnetic map, because here on the domain we have psi itself, and here we have the magnetic structure defined previously via the Kähler two form. And what we have to do here, we need F star, okay? But our F is psi, so we need first to compute the differential of this map, the differential of psi from M to Tm. So we have this is again a classical result, it's not ours. So we have this. psi defined on X. Okay, we are working between tangent spaces. We have the horizontal part plus the vertical part. We notice that here appears the covariant derivative of psi. And we recall a very known result, which is related to my previous remark with respect to isometric immersion, saying that a map psi from M to Tm is an isometric immersion if and only if psi is parallel. So it is very strong. So we continue to ask when a vector field is a magnetic map. So we consider first the compact case. So if M is compact, the energy of a vector field is computed like this. So we have the volume of M multiplied by n/2, and we have this integral where the covariant derivative of psi appears. This number is called the total bending of psi. And again, we have a very nice result of Ishihara and Ho, saying that psi is harmonic map if and only if psi is parallel. Okay, so the same condition we found before, and this is strong. And in this case, this part is 0, and it is an absolute minimum of the energy functional. So this part remains. Okay, so recall that harmonic maps means that, so from the definition, we make the variation through all maps from M to Tm. Okay, all maps, not only vector field. And Gilles Medrano extends the previous result. So said, okay, let's do the variation not through all maps, but only through vector fields. So the variation of psi, each variation will be a vector field. Unfortunately, the same condition holds. So psi should be parallel. Okay, so what is needed to do is to take the arbitrary case and to compute the tension field. Okay, and if we compute the tension field of this map of psi, it is obtained this. So a good reference is a book of Sorin Dragomir and Domenico Perrone. I think most of you know or at least heard about this book. And we have this formula. And what we notice here, so the curvature appear here, and the rough Laplacian for vector fields here, and the horizontal lift and vertical lift. Okay, so we are interested in to answer the question when a vector field is a magnetic map. So we have this result. It was obtained in some steps, and so we have this result. If psi is a vector field and psi is a magnetic map associated to psi itself and with the Keller magnetic field omega s, if and only if this condition holds. So let me briefly explain this Q. So instead to work with QS, we work with Q omega s. This is a constant, so this does not affect the quality of omega to be closed. But it's better to interpret this as a magnetism of the magnetic field. So in general, Q is 1. but we will see how important, in fact, we know the importance of this Q from magnetic earth, but we will see also here the importance of this Q. In which sense? We, if we put one, we are we have a lot of constraints. If we let Q to be arbitrary somehow, we can obtain several values for Q in order to obtain some geometric properties. So in order to have non-existence result, we have an existence result for a special parameter value of Q. Okay, so for this reason we put also Q. So let me look here. So first is the trace of the curvature with some arguments here, and in the right-hand part, we have the covariant derivative of psi with respect to itself. And here we have an equation that says that psi is eigenvector of the rough Laplacian, and the Q is, or minus Q is eigenfunction that should be constant. Okay, for the proof is almost immediate, because we know the expression of the tension field. In the right part we have this one. So this is Lorentz force. So that's the phi multiplied with the Q. And here we have the horizontal part and the vertical part. They are independent. We will split also here into the vertical part and the horizontal part, and we put equality sign between the corresponding components, and we obtain the previous equation. Okay, so because we have here the curvature, if the curvature tensor has a particular example, a particular form, or at least a concrete form, this equation can say more. And for example, if M is a space form, so its sectional curvature is constant C, the expression is this one, and the trace has this form. And we can develop here. You can exploit this equation, and you can obtain several information for psi. For Sasakian space form, that means C is a constant phi holomorphic sectional curvature. The expression is this one. It is complicated, but it can be used. And we get that the first equation is automatically satisfied, while the second equation leads to this one. So for psi to be magnetic, the strength should be precisely minus 2n. If Q is different from minus 2n, we do not have the magnetic property for the map. Okay, so this explains, for example, the reason for which we choose Q. Okay, so this is one point of view, but we can work with unitary vector fields. So these are, or at least with vector fields of constant length, we will work with unitary vector fields. So these are sections from M to T1M or TRM. And TRM can be thought as a hypersurface of the tangent bundle, given by this equation. And the normal vector field of TRM into TM is this one. So this is the Liouville, and we want to normalize it. G bar is the induced metric from the Sasaki metric in TM. And because the horizontal lifts are tangent, but the vertical are not tangent, so we need to project the vertical ones. So we have here, if the dimension of M is n, the dimension of Tm is 2n, the dimension of TRM is 2n minus 1. So we have n horizontal vector fields that are independent. We have n verticals that are not tangent, but when we project, we obtain n projections, but they are not independent, but they generate a n-1 dimensional space. So it was Boeks and Van Hecke that defined the tangential lift, so from M to TRM, defined in this way. So they projected it, and the tangential part, so this is precisely the vertical lift projected to the tangent spaces, and the tangent space at U of TRM is generated by the horizontal and tangential part, with the property of for this Y to be orthogonal to the point where you make the lift. Okay, the almost Kählerian structure of TM induces on TRM an almost contact matrix structure, and it is defined in this way as naturally as on every hypersurface in an almost Kählerian manifold, and we see that the contact to form, or the fundamental to form on TRM, is this one. So R is constant, 2 is constant, so we have it is exact. So again, it is a candidate for a magnetic field. Okay, so this last part of my talk is very recent work with Junichi Noguchi from University of Tsukuba in Japan. And the manuscript is submitted 2 years ago. And what do we have here? So we have this this possibility. So we have this map from M to UM, to T1M, and we consider the lambda hole functional, and we make the variation. We can make the variation through all maps, all possible maps from M to UM, or we can restrict to the unit vector field, denoted by He1M. Okay, so for harmonic vector fields, for harmonic unit vector fields, if we make the variation through all maps, the vector field should be parallel. Therefore, the good definition for harmonic unit vector field is to make the variation through unit vector fields. Okay, so not through all maps, but through maps that are unit vector fields. And if you compute, you obtain this one. The rough Laplacian here is the norm of the covariant derivative. And so the rough Laplacian of x is parallel to x with this factor. Okay, so we want to do the same with our problem. So let me pass this one. So we compute the variation. Okay, and if we compute the variation through all maps, we obtain an equation. So we obtain the equation of a magnetic map. But if we make the variation through unit vector field, we obtain this result that says that this equation holds. That means X is a harmonic unit vector field. So we return. So we obtain nothing new. Therefore, to define a magnetic unit vector field is not good to make the variation through unit vector fields, but through all maps. So here is a tension field. It is it is different from the tension field defined when here we have Tm. Okay, the target manifold is different, but the formula is again computed in the book of the Dragomir and Perrone, and also by Han and Lim. Okay, therefore we have this this result, a unit vector field, so from M to UM, is a magnetic map if and only if this part involving the trace of the curvature and this component appears equals q nabla xx, and this equation that appears for unit harmonic unit vector field. So both, as in the case of TM. Okay, so if we want to work, let's say to follow formally the computation for harmonic unit vector field, this fails. Okay, so so this is the proof. Okay, so what we want to say? So a unit vector field is a magnetic map in UM if it is critical points of the lambda Hall functional under variations in He1M together with, so this leads to the second equation, and together with this equation involving the trace of the curvature. And we finalize our study with giving examples. So we are working in Lie groups of dimension 3, and we consider the unimodular and the non-unimodular cases. And we developed these two equations in order to say to classify magnetic maps from or unit vector field as magnetic map from G to UG. Okay, so I will skip this. Okay, so in 1 or 2 more minutes, I will give you 2 other examples of how the energy of a map is can be perturbed. So other definition of harmonic maps with potential. Okay. In this case, it is defined a new energy functional. Here, other spin bundle appear, a twisting Dirac operator, and I kept the original notations. So the 2 form is denoted by B, and the energy, the new energy functional. So they call the new energy functional. So it is the energy plus this part which plays the role of a potential, and the critical point of this new functional is called the magnetic Dirac harmonic map. And the second example I want to point out here is this perturbation. So again, a new energy functional. So here is the energy, and here is the potential part. So we have a scalar function V. Okay, so this phi is mapped from M to N, and then we apply V to map in R. So this for each point, and we obtain a function here. So we integrate and we obtain a new energy functional. And if we consider the critical points of this new energy functional, is we obtain this equation. This notion was introduced by Fardun and Andrea Rato a very long time ago. And our plan is to see if there is a connection between our definition and this. So between our psi, so this is important, our psi and this scalar function. My impression is they are somehow connected, but until now I didn't obtain anything. And I want to mention also the name of Volker Branken, who works in this area. And thank you for attention.
Okay, thank you, Professor MUNTEANU, for your nice talk and giving information for us. Now the time is for asking question. Is there anyone who wants to ask question or any comments? As I told you before, you can use the question and answer button, or also if you want to use your microphone, you can raise your hands.
I think I can say teşekkürler, no?
Teşekkürler.
Here, no?
Okay. Evet. Professor Inan Ünal says, thank you very much, Professor. It's really nice talk.
Please.
Yes.
Is it possible to ask?
Of course.
Okay. My question is about the second variation of the magnetic curve. Thinking in geodesic, it's natural to ask about what is when geodesic is the minimum of the energy. For example, the existence of conjugate points, etc. What about here? What you can say about the stability problem or the second variation?
I just started to study the second variation for magnetic curves, and maybe 1 year ago. In fact, my intention was when I visited you, I don't know, 3 or 4 years ago, but I stopped. And now I started to obtain magnetic Jacobi fields. There are very few results in these directions. Some results are done for Keller ambient space, and we did for Sasakian and for cosymplectic ambient space. So the first we obtain Jacobi magnetic field. The next problem is to obtain to obtain some comparison in Kellerian ambient. Something is done by Adachi, Bao, and some people from Japan and I think Korea. So it is I can say work in progress.
But thinking in Euclidean space, for example, the problem I suppose depends on the function phi.
Depends on the sure.
Okay. And then, for example, in Euclidean space, what are the interesting function phi to study or to begin to study the second variation problem? Sorry, the stability problem. What are the interesting forces phi?
In Euclidean space, maybe the most interesting comes from constant vectors. Okay, because this phi is, I'm afraid I cannot write.
Not necessary.
Let me write something here. Okay, it's something like this: B, a constant vector, times something. Okay, so phi of x is B cross x. It's a vector cross product, and this B is constant, for example, or it is rotational. But for rotational vector fields, also the magnetic curves are very complicated. Elliptic functions are involved. If B is constant, we obtain lines, circles, or helices.
Okay.
And for Jacobi fields, it is not, in my opinion, is not so interesting. So Jacobi field themselves, but the comparison, I don't know. So the stability problem is not yet, I don't know yet.
Okay, thank you.
Maybe next year.
Okay, Professor, I have also 2 questions about your presentation. First one, I think, is a fundamental question, but maybe you explain it. I skipped it. We know the geodesic maps give the shortest way, as you say. What about the geometric meaning of magnetic maps? Does it have some geometric meanings?
Yes, but there are, I will I can say you other things. I will not answer you directly to the question, but I will let me type here. Maybe it's better if you. So there are some studies involving both magnetic maps and geodesics, and that are called, let me, harps and horns. And I will explain you the meaning of this. Let me move this. Okay, I think it can be okay, harps and horns. So what do we have? So we have here. Let's start first with the magnetic curve. So we have a magnetic curve with fixed initial point and let's say more or less fixed endpoint. And you start with the same initial point with a point on the magnetic curve, and you connect these 2 points by a geodesic. This you move to other point on the magnetic curve, and you connect again this one, and you obtain like a harp here. Okay, and again, Bauer and Adachi studied this the geometric property of this harp, and they said a lot of information of the geometry of magnetic curves. For magnetic curves, you have some properties for with respect to the curvature, because if the geometry of the ambient space is nice, I mean Keller or Sasakian, and also cosymplectic, you obtain the constancy of all curvatures. For example, me and my collaborators proved that for Sasakian and for cosymplectic geometry, you can reduce the codimension until so far as the magnetic curve lies in the 3-dimensional manifold, endowed with the Sasakian, respectively cosymplectic induced structure. So essential for magnetic curves in Sasakian space forms or cosymplectic space forms is dimension 3. But if you move to quasi-Sasakian, so if you enlarge a little bit the geometry of the ambient space, the property is no longer constant. And we in dimension 3, the curvatures are not necessarily constant. Even that I found some wrong papers saying the contrary, but we prove that it is not true. So we furnish also examples from dimension 5 and more. Again, the constancy of the dimension of the curvature is true, and we claim that everything can be reduced in dimension 5. We make it is a paper myself and Anna Nistor published this year in nonlinear analysis, I think, where we make a kind of conjecture that we can reduce everything in dimension 5 for quasi-Sasakian. We furnished some examples, we sustained this claim, but we were not able to prove.
Okay, Professor, thank you for your answer.
And the second?
Yes. The second one is about the finite type theory. Is it possible to apply finite type theory on magnetic maps? Because you give some relation with the mean curvature and the magnetic maps.
Probably because also the rough Laplacian appears there. I don't know. I never checked. Probably. I have no idea.
Okay, thank you, Professor. Thank you very much again for your nice talk.
Thank you, everybody, for listening And
Okay.
okay.
Okay, now Professor Babarslan wants to say something, I think.
Hello, Marian again.
Hi.
Thank you for your nice presentation.
Thank you for invitation.
I hope that we will meet face to face in the future again. Greetings for your wife and children.
Okay, thank you.
Thank you so much.
Okay, thank you.
Okay, thank you again. Dear participants, we will have a 5 minutes breaks. After the 5-minute breaks, we will continue with the Professor Yildiray Ozan. Thank you again, Marian. Thank you, Professor.
Thank you for invitation. See you. See you.
See you.
Soon.
See you in Turkey.
Or here.
Okay.